So we can talk about the next one now, which is 1.3, supervision in machine learning. So in general, machine learning can be classified into supervised or unsupervised learning. And on that supervised learning, the data is pre-classified with labels, right? So here you can see we have some blue data, mostly in this area, but not exclusively. And then we have some black data points. And that's supervised because I've got labels on them. So I've got them color-coded here with labels. And so what I can do is I can try to build a classifier in between those two labels, right? And now, if I have a single classifier and I were to give you a point here, right, is that going to be blue or black? And the common answer would be, well, it's probably going to be blue, right? Because it's on the blue side of my model. So that's a supervised learning job. I also have unsupervised learning. And here I'm just going to give you training data, and it's all gray, right? I don't have any labels. I don't know what the labels are. But I could run something like a k-folds matrix, and I say, well, you know, I kind of have 1, 2, 3, 4 clusters. Then once I build my clusters, I can define them with some boundaries. Now, if I give you a new plot here, I can tell you it's red. But I don't really know what red is. It's just different than the others, right? So I don't have any supervision that's going on. So when we talk about supervised learning, (1.3.1) supervised learning. This is generally what it looks like. You have some amount of supervisors that are feeding in labeled observations, and then you're going to end up with a training set and a test set, and we're going to build a machine learner that will kind of classify off of your two sets, and then on the output here we can have some final results. Yes?
So like, I get how this works for like classification. Is there such a thing as like unsupervised regression, or does that not really make sense? Is regression not like supervised or unsupervised, or is it all supervised? Or is that just not really a terminology for regression?
So regression is going to be supervised because you're feeding in it known data and known labels. So regression is going to be a classified because it has labels.
Is that because like the labels kind of like are the outputs?
The labels are, yeah, like the price of a house.
That makes sense.
Yeah.
So there is no like unsupervised regression.
No. Yeah, regression would be a supervised algorithm. So regression would be a supervised algorithm. Because it's a relationship between the dependent variable, your output, and your more independent variable. So if I look at like a regression here, I'm going to have an output, and then I'm going to have an input variable. And here you're going to build a model, right? So this is model based. A lot of these algorithms could be classified a number of ways, like model-based, instance-based, class of supervised, unsupervised. So I'm trying not to like give you the just jump to an answer, I'm trying to think through it. We can list out a few important supervised learning algorithms, right? So we have a K nearest neighbor. Linear regression. Maybe logistic regression. Support vector machines. Decision trees and random forest. And maybe some neural networks. Not all, right? You can have unsupervised, supervised. That can work either way. So (1.3.2), let's go over unsupervised learning. And then maybe comparing and contrasting the two will help the thought process unfold. So unsupervised learning, you're going to have something like clustering. And that's the process of identifying and grouping similar points together in a larger data set. You might have something like association. And that might be things that are different but are associated together, right? You know, socks and shoes are not the same, but if you have a pair of socks, you probably need a pair of shoes. You need 2 socks, you need 2 shoes, but you only need 1 shirt and 1 pair of pants. So there is some clustering there that can happen. Some association there that can happen, right? You need 2 shoes because most people have 2 legs, and you only need 1 shirt because most people only have 1 body. So also dimensionality reduction. And that's the process of reducing the number of input variables in training data, right? So a good thing to do, you know, a lot of times what you might do with an unsupervised learning is you might do some basic clustering. As a form of a data exploration, right? So here's Barack Obama's first inaugural speech and some of the words that he said, you know, new nation, America, generation, people, must, common, greater. This is kind of a classic clustering, unsupervised learning approach, right? We're just trying to look at what things are said together and what things are together. And out here you have 3 things that are on their own that, you know, the algorithm decided were not clustered to anything. And they are college, school, and university. They are all the same, but different than the rest. So at least kind of in terms of words. So
Are dimensions the same as features? Like when you're looking at data.
can be, yeah. Yeah, dimensions is probably like features would be inside the Venn diagram of dimensions. So another thing in unsupervised learning, right, you might be trying to kind of learn more about your customers, right? Say that you're working on like building a YouTube channel or you're working on selling goods and you might realize that, well, most of your customers are, you know, If you're selling luxury homes, you're probably not selling to a lot of homeless people, right? And if you're selling burgers on the street, you might sell to more homeless people. Neither of those is bad, but some of what we can use unsupervised learning for is trying to find those associations and put them together, and we can kind of use them for better understanding. When we come to understanding, we want to talk about visualization. Algorithms. Which can be very important for instances of unsupervised learning, because they'll take these extensive, complex, on-label data and produce nice 2D and 3D representations of the data, which then allow us to kind of understand what's going on in the data. So I'm going to show you 3 different flowers here that by the end of the class you will know very well. And these are a famous set of flowers in machine learning. And they are the iris flower data set. And there's 3 species of these flowers: Setosa, versicolor, and Bergensia. And so there was a botanist who went out and measured these 3 flowers. And you have in a flower, you have a sepal, which is this bit here, I believe. And then you have a petal. And he measured the length and the width of each sepal and petal. And then you can use these to kind of figure out, if you were to find a flower in the field, could you use it to figure out which of these species it is, right? And people have been playing around this data for a long time. So we have lots of imaging for it. One of my favorite ones is just a visualization, right? This is not scientific. It's not supposed to be scientific. It is a subway map of those 3 flowers, right? And basically it's trying to tell you, how do you use a subway map? Like a subway map of New York, it's not at all the shape of New York, right? If you look at a subway map of New York, all of New York City is Manhattan, because that's where all the subways are. But if you look at New York City, very little of it is actually Manhattan. So same thing here, there is no dimensionality, but what you could see is your iris and your versicolor, these 2 are close to each other. Agreed? Right? And it may be this stop on the subway, there's a little bit of each, right? So it could be either or, but there just tends to be more iris here and more versicolor here, right? Maybe you're in a part of town that has more hot dogs and another part of town that has more hamburgers, right? So, but they're close to each other, but not quite the same. And then all the way out here, you have something good like Mediterranean food or something, right? So you can see that my iris certosa is way out here on its own. I don't need to know anything about flowers to know how to read this map. Make sense? So it's a very good tool when you're talking to non-experts in the field. Now, if I give you my length and my width of my petal and my sepal, can you tell me where it is? No, right? It doesn't have that amount of information. So for that amount of information, I might need a better classification. Which might look like this, right? And now I've got my petal length and my petal width. I just have 2, we're just looking at petals. We kind of drop sepals here. And I know that my certosa, right, which was my yellow in the last plot, is way out here on its own. So if you give me my petal width and petal length, and I could probably figure out if it's a certosa. If you give me the petal length and petal width, for a good chunk of it, I can figure out if it's versicolor, and for a decent chunk of it, I can figure out if it's Bergensia, right? I guess maybe here in the middle, we don't really know. So the problem becomes, if you give me something that's here, I'm not too confident, right? I couldn't make a confident prediction of what you have. This is another good visualization tool. but it's not going to get me all the way, where I want to be. Another good tool is anomaly detection. And anomaly detection might look more like this. Right? So I've got all of these features in my plot here. And I've got a nice normal data point, and I can just get my center of all of my features, and I can measure out to all of my data points. But this one out here measures too far, right? And because it measures too far, I can classify that as an anomaly. I know nothing about the data, right? It's an unsupervised approach because I don't have to know anything about the data for it to allow me to understand the data.
Professor, what dictates the threshold of points considered too far? This is a very obvious example, but not all data looks like that.
Whatever you want it to be, you set your threshold. So
you set some range not fair.
that's why you are an expert in your field, right? That's why we have to learn how to use the tools properly. So 1.3.3 semi-supervised learning. So among certain algorithms, we can leverage a little bit of the strengths of both, and we can create semi-supervised learning. So here we have two classes. We have class A and we have class B, and those classes are going to be supervised, right? I have labels for them. And then I have an unsupervised data set here where I don't have any labels. I'm going to have feature 1 and feature 2, and I can start to say, well, you know what? Even though I don't have labels for all of that data, I bet that's all going to be class A. And for here, I might not have labels for all of this data, but I bet that's going to be class B. That makes sense? So I can create semi-supervised, right? Instead of me having to go out and manually label everything, what if I just label a few of them? Much more efficient, saves time. Is there a risk that something might be misclassified? Yes, but the offset in terms of training and labeling and all of that work might greatly outweigh it.